Hello, everyone.
Morning.
All right. Um, Looks like they might have a different meetings today, so that's why attendance was low. Jeff, is there a different meetings?
I'm not aware of any other meetings this week. Next week there'll be an IEEE meeting.
Oh, next week. The AO2
Yeah, it's a plenary, so I think they're meeting in the East Coast somewhere.
mm-hmm. Um so um I think since we hadn't finished the discussion with Karen's presentations, I think we can continue that a little bit. And I before that I'd like to um I'd like to share my plans for the next couple of weeks that what I will do is um since we've been decided we want to do the scale up network and recently UA Link is about to announce their 1.0 spec, so which is about time to they probably will release it soon, maybe in the next couple of weeks. Um, so I'm planning what we can move on next, and what I'd like to do is try to get connect with UA Link, Bijuan and Cliff. Try to organizing this from the OCP perspective. We'll get connected with the UA link, and what I hope is we can um, ask the UA link to come out with a problem set that they have, so they can have even don't even need to be a lot of it, to just maybe a page or two page of PDP slides, and just mention uh, maybe several points of bullet points of the problem set that they think it's better to overcome, or the challenge would be, and then we can um, addressing that from a different technology perspective.
Hey, Bobby.
Um, yes.
Hi, this is Ren. I don't think UA Link right now even talking about anything about optics within that group, right? So I'm not sure
Yes.
when you say problem, what do you mean? I mean, they don't even talk about optics. So I
Exactly.
think it's more
Because
about
what I
how do we
think,
use optics to extend their, I guess, coverage.
yeah. I think they will definitely need that, right? Um, because when I browsing the UA links back, it's mostly about the electronic connections, and more on the protocol spec and how the network architecture is supposed to be. But to connect 1,000 nodes, um, 1,000 nodes, it's definitely not something that you can uh, compress into a rack that everything can relying on a copper link. So it has to be optics somewhere. But but they, I mean, they must thought about it before, right? And they probably didn't put it into the spec because they want to be flexible. That um, does not the spec does not tie it into a certain implement way of implementation. but they must thought about, like, what is the trade-off, what is the key pivot point about the trade-off, and that's what I hope that uh, they can reveal those uh, thought process, right? The thinking point, and then as a short reach optics group in here, we can using that as a guideline or the first chapter um, to to address the problem with optical solutions.
Yeah, no, I definitely support. We should work on optics to make sure that 1000 GPU can be connected.
Yeah, right. So great, Bijan's here. If we I was talking about that since UA Link is about to release the 1.0 spec, I think we can maybe get connecting to Curtis Bowman to see if they can help us to give us a slide or two, maybe come to stop by to present it a little bit about the challenge to connect a big network and what do what are they thinking about how's the UA Link um, network's going to implement it.
Sorry, I was on mute. I was talking. Yeah. So I think that yeah, we can connect with Curtis, no problem. We have also some other board members like DJ from Meta and Amber Hoffman from Google on the board. Um, what we what I think is that you know, you have you have a question and then you have, well, there's two questions on the table. One of them is, what is the best interconnect for short reach, right? And then the second one is, what do you have to do to make UA Link successful, or how could it be implemented? I guess the right way to say that. So I think there's two questions here on the table, and I think we started, earlier, kind of exploring all options, going down all possible paths for the first question on what is the best possible interconnect. But I think where we maybe spent more time than we should have was we were only focused on what was available, right? And I think what we should probably do in light of this UAL question is that kind of, take on the first question as, what is the ideal thing that's required, right? What's the best thing? Irrespective of what already is out there. So, we all know what PCIe can do and CXL and, Ethernet at this point, blah, blah, blah. But I mean, there's, is there a magic number for, escape? Is there a magic number for beachfront? Is there a magic number that would allow, a higher level of performance from, CPU to GPU, GPU to GPU, GPU to memory, that kind of thing? Or are we good? Is UA Link all we ever need? So I think, to me, those are the two essential questions that we should answer here.
Ryan, have you
Yeah.
heard any rumblings in the industry on how UA Link is being received at this point?
Well, there's a commercial aspect to this, right? A market angle, as always. And so UA Link is definitely, from a market point of view, there's a lot of pull from companies that wish to have some alternatives to what's on the market today. So there's a lot of interest. There's a lot of interest. Everybody I talk to basically is interested in it. So I do think it's going to be, it has the potential to be a hit, but they have they have a lot of, I don't know, it's going to be a challenge too for them, because to make it successful, they're going to have to deviate from pure Ethernet specs in some way. So we're going to see a little bit of fracturing here. And this is just me, crystal balling. It's not anything I know for sure. And so now the question is, which market entities are willing to take on this, to build for this kind of, divergent spec or whatever. So I'm curious about that. But to answer your question, Jeff, there's a lot of commercial interest out there.
No, that's good to hear. I've just heard some rumors lately that UA Link isn't doing so well. And part of the reason is that there's so much more progress on Ethernet PHYs and FECs and stuff that the lowest common denominator in the industry is to reuse as much as Ethernet as they can.
Well, that's kind of why I said we had two questions on the table. Yeah, I'm not, I agree with you. I think there's a lot of, no, I wouldn't say a lot. There's been some voices that have been out there that have been questioning, like, do we need to? So there's market interest in, bringing things to market. There's, technical interest in, is this the right thing to do? Or should we stick with the other things that are already existing? And I totally agree with you.
I think from OCP perspective, I think we could, I mean, if we want to work on this, not necessarily just for UA link, right? Because on a physical layer, from like most fundamental PHY layer, like a baud rays and all that stuff, probably is common enough. We could just focus on up, this is called a scale up optics, which can actually do both, right?
Agreed.
And obviously, one of the big, I guess, public problem for UA link is like Broadcom just dropped down, right? I think that's a big hit.
Yeah, I mean, they were kind of being forcibly pulled. They never really wanted to go the UA link direction. But one of the massive customers was pulling them into doing it. So this is a very curious.
Brian, I think every so often your microphone cuts out. At least that's what it sounds like to me.
I also have some. I don't hear anything anymore. The link is lost.
Yep. Great. Glad everyone was discussing about this, and I think if you have any thoughts and idea, please let me know, and Bijan will discuss more offline about the how to collaborate and invite people. So we still have 15 minutes. Maybe we can continue to discuss about the Karen's slide.
Hi, Bobby, did you send Karen's slide to members?
Yes, I did. And if you did not get it, let me post the link in here.
Yeah, thanks.
Karen, do you like to share it again, or share the screen, or I can do it on my side?
Yeah, why don't you do it on your side?
Okay.
Because you just posted the link.
Share my screen. So see the slide and let me minimize this. And last time we are going into these slides, and then I think we kind of stop in somewhere around here. And so this is about the density for existing connectors, and I think I remember we kind of stopped here, right? We were talking about if we have 2 rows, then the SI could be a problem. So that's what we kind of stop in here, and I'm wondering if we have Amphenol at the same time, people was able to address a little bit more in help to address more in these slides, because certainly like to put more informations into SI simulations, maybe the on the PCB or other things to show that if this ultra short connections, what will be the possible or reasonable distance in the next couple of years of development.
Well, I guess one question is, this presentation showed 2 use cases. One was on board and one was on package, essentially. Are we going to address one or the other here? I mean, I think it's a question of which, are we doing both? Are we doing one? If you go to the next slide, for example, it's actually.
Yeah, that would be, I think I'm open up to the larger audience. Because I think
So I mean, it's actually not called out here, right? Use case 1 in this presentation is on board, but actually this board is ambiguous. It could be a substrate, it could be a PCB. So there's actually kind of use case 1A and 1B. And then use case 2 is what Ryan alluded to, which is front panel pluggables. But the other end would, might be the CPC or something.
Yeah,
right.
so Karen, my comment, Bobby, my comment here is OCP is about open, right? So I think we should not exclude the options at this point. I think we should open even soldered down version or open socket or pluggability and look at the use case for all of these. But the key here is to have an open ecosystem here, right? So that's my take here.
Yes, I totally agree. I think that one of the original thought in my mind about this white paper that we like to present is all about, we have a problem, right? Then the problem is we're gonna scale out so many things, and like Bijan mentioned, and what would be the ideal case for each breakdown and all other different things. And then we're open to any kind of solutions that either you can do front panel and you can list it out, but and you can also, there's always different technology always has different trade-off, and we're just listing out all the trade-off in here, and
But it's important. But it's important to be somewhat technically rigorous to see each option what is the true limit, because there are lots of, I would call it technical rigorous, but also lots of marketing promotion to sort of bash one against the other. I would say in this community, we should be more technical rigorous to look at what each option can, I guess, bring the benefit to the application with a reasonable assessment of density or bandwidth density in 1D or 2D, beachfront limitations. I think we need to do enough analysis to kind of help the community to make that conclusion. Like
Oh,
if
definitely.
you're 10 terabit per millimeter, maybe you can forget about socketing, right? But if it's 1 terabit per millimeter, maybe you can still use socketing, right? That kind of, I guess, I would call it objective analysis is very useful and helpful to the community.
Well, definitely, definitely. Yes, yes. And that's what I love to see, we can, the team member in here would be able to help contribute, we're all based on numbers to talk about the story, right? And help the whole OCP to navigate the directions.
Yeah, I see a problem is actually for system designer, it's hard for like them to make a quick assessment of what option is available. So often they just somewhat biased by whoever come in to pitch idea to them.
Yes,
I also think it's very helpful to lay out all the different options clearly because terminology is a little fuzzy, right? I mean, what's a
Yeah,
chip?
yeah,
What's CPU
I
exactly?
agree.
And so I think if we have a good white paper and people can say, what I mean is category 4 in the OCP white paper, right? It's like, oh, okay.
Right,
oh,
right.
yeah.
And
That was,
also there's some good technical information is the channel loss because many of these analysis channel loss is a very critical parameters. So depends on, I guess, your how you stack up your chips and layout of your system board. You have again number of layers of loss elements. So we also need to be somewhat rigorous layer there, right? Because like it's CPO, MPO, one versus the other. At the end of the day, it's like, what is the limitation there for CPO versus MPO, right?
True.
And again, these words got thrown around, but I think we need to be more rigorous on how these different options, again, limits that density and also channel loss. It is important to also look at the options of flyover cable versus, PCB or different PCB material and how many layers you stack up on the package on board. I think all these are very messy right now. I actually think it will be very useful and very helpful. This white paper can actually help to be rigorous technically.
Yes, yes. That's a wonderful suggestions and plan out for the paper. We like that, Ryan. So yeah, I hope that the community here would be able to help in more about that for sure. And let's try.
I can volunteer, maybe, maybe send some, maybe sketch something out for next discussions.
Oh, wonderful, wonderful. Thank you, Ryan. And we can talk offline and chat a little bit more to work together about that. Thank you. Um, so I think this is the this pitch things and it's all about the packaging design and there are still some I think this is my guess is it's from the OIF discussions. I'm not
Yeah,
sure if
this
it's
is borrowed from the OIF discussion that Peter Windsor presented. So it's just talking about um, just a picture of what's involved, right? Like when people consider these densities, I mean, I think one thing that is a good example here, right, is granularity, right? If you have a larger, if you aggregate a larger area, I mean, this is not the point of his slide, right? But what I took away in our context is because you always have to have keep outs around for example,
Yes.
LJ pad, right? And then in fact, what's not shown is you have another keep out between this chip and the next chip, right?
Right.
Then aggregation is useful. Then there's technical limitations to how much you can aggregate, right? So that could be another limitation that we would want to articulate, right? Is that, because of chip warpage or package warpage or whatever, or accuracy of BJ landing or LGA landing, that you can only have, and realistically up to an X size, which means you could only aggregate so much, and then you need this extra overhead or something. I don't know. I mean, I think that's really
Karen,
here.
Yeah, Karen, I do have a quick question here. I think for customer to look at this 2D socket map, I guess one of the key questions for them is to route the signals, right? How do they route the signal, especially is on board, right? Have you considered this?
I don't want to get caught up in this whole 2D layout discussion, right? I don't think that was the point here. I think the point.
Understand? Yeah, I'm just quick question here is that a limiting factor, right? Like when you have a very dense 2D grid there, signal need to be routed there. So I'm just say that need to be part of that practical.
I think that's right. I think that's right. I think that's right. I think whether it's a large chip or whether it's two chips, adjacent, the routing is a limitation that needs to be taken account, and it happens in a plane sort of into the page here that we're not seeing, right? So I think packaging is very important when we talk about limitations. One of the questions is, what's a realistic number of layers depending on, if it's PCB or substrate. We haven't
exactly.
Really
so that's part of that
right?
conversation, I think.
Exactly.
Yeah.
Exactly. So I think I was just going to ask if, the people I see on the call, I think we all work with the people that work on these, materials and technologies. But are there other projects in OCP that we should be referencing for development of PCB materials, for development of, dense routing?
We could certainly collaborate with other, groups that are dealing with this, like the server group, for example. Yeah, that would be a good idea. I think, just kind of a liaison across the, to their project, and, invite their, subject matter experts or whatever to kind of help us out. I think that would be good. Good idea.
Yeah, Bijan, that would be great. Particularly, I like I said earlier, this whole thing need to be look at like end-to-end kinds of view. Otherwise, very easy to just look at one element and then not consider other constraints.
Totally agree.
Yeah. So
this is more of the same, right? I mean, this is, what is the pad pitch limitation based on your technology? So again, having those subject matter experts that we can draw
and then we have many different options in here. I think this supply voltage could be an interesting one to discuss, because how to minimizing the current, bring it in, and increasing the conversion efficiency. That would be a important part of the overall efficiency. But to bringing the power conversion circuit into the module, that could increasing the additional components inside, and I think that also means you need a probably a larger package in it.
Hey, if we're gonna write a white paper, and someone had, I think it was Karen or someone had some great suggestions on standardized, putting some reference material in there so that we could all agree to what the terminology is. Let's is it possible for us to define what we think the correct way to determine power per bit is? This number is so hard. There's so many different ways that people measure it, and it's all over the place.
Ishan,
Yeah,
do you know what some of the main differences are in the way people do it? Because I think in the Ethernet world, it's pretty standard, I think.
I've seen it measured like at the amplifier. I've seen it measured in the link. I mean, it widely varies, right? Like,
Mm.
some people take all of the you know, link impediments and consider it. I mean, there's just multiple ways of, and mostly it's people advertising their product. But if we don't have, we just need to standardize. I mean, if someone has already
Yeah.
defined what it is, let's say use this.
Mhm. Okay.
No, I think
Yeah.
Bijan raised a good question. Again, if you're just looking at module, right? So this is on this page, it really just define module. But at the end of the day, I think we need to define sort of bump to bump, like just start from the whatever ASIC chip coming out all the way to complete the link. I think that's a different way to do it. But I think that's a little bit rarely seen that way, but I think that's the way to do it, because otherwise you can move this power around different places, right?
Exactly.
Mhm.
And it's hard for system developers to kind of understand what they're working with right now.
Yeah,
It's
I agree.
possible. It's possible there's multiple definitions, right? I mean, one could be,
No, Karen, you're right. I'm saying we should define a
we
link
should
level.
define, yeah, we should.
Yeah.
I think we can, because there's certain things that are, total power, right? The whole total link power is very useful from a system perspective of, you would sum up how many links there are and get an idea, right? And then there might be something else, which is power inside some confined space, such as a module. You know,
Yeah, make matter more complex is very much the SerDes, the front end SerDes is determining a lot of these power numbers.
right.
So
And I think it's an important part of, one personal, situation I ran into was that when you have AOCs, for example, no one's really accounting for that power either.
Again, they just looking at narrowly, right, that module to module loss, but not really end to end, because now you had to have a retimer somewhere to drive that.
I
And
think,
depend, yeah.
but I think the problem is if you do that, then there's the question of, is it 5 nanometer or 3 nanometer? I mean, there's all sorts of other forks that you have to take, and when you think about it.
Well, maybe
I
you
think,
just
yeah.
you point to the measurement, like how to make the measurement. You don't really be prescriptive into what to measure, maybe. I don't know.
No, I think Jeff again brought up another good question here. I think we had to reference it properly, right? If you start to think this number as a black box, then yeah, then start to argue that is it 5 nanometer, 3 nanometer, 2 nanometer. I think it's definitely a big factor. Whatever the silicon node you actually implement these links.
yeah,
Start
yeah,
from
I
SerDes.
do agree that that the DSP node, plays a big factor here, because especially if, let's say, you take 100G DSP, which is done in 5 nanometer, and build a 200G DSP, you're doubling the gigaflop there, So yeah, obviously the power will increase, So I think that's true, because we haven't really seen CMOS evolution applied yet to, and also design improvement really applied to 200 gig yet.
Yeah, complicating that choice also with the CMOS node going down, power envelope not necessarily getting better in our world, right? You start to see like the power actually goes up. So those are the factor I think we do need to consider. For example, now with this 3 nanometer come out to support 1.6T, the total power actually go to maybe 24 watts for 1.6T, something like that.
Right,
So
right.
the
That's right.
improvements start to get very, like compared to 800 gig, I think we are already start to see maybe 13 watt or something. So it's actually not necessarily go to the next generation. The power per bit goes down actually.
Well, I would say that, yeah, even if you look at, the power of the DSPs, like for example, the 1.6T versus, as you said, 800 gig, which is eight lanes, is roughly, it's about double. But again, that's done in the same node, and there hasn't been like a design improvement yet. So I would expect that, just as we have seen in the past, we will see, I do agree that, is it slowing? And for example, and maybe on some of the analog, it doesn't improve as much, but we will see that power, improvement in 3 nanometer.
Yeah, yeah. No, I think fully retime to fully retime is true. What I'm just saying is I guess percentage of DSP burn in a whole interlink start to become a bigger portion because the optics, when you double the speed, it doesn't really double.
Yeah, that's right.
Power.
Exactly. So I do agree that, for example, a laser to power, let's say an MZM, probably costs you 1.5 picojoule. And that 1.5 picojoule, it doesn't matter if it runs at 25 gig or 200 gig.
Right. So yeah, I actually start to see, ironically, go to 200 gig customer more interested in linear optics now because they found, oh, gee, that's DSP burning so much power.
Yeah. So I think but I think we also have to be, pragmatic in terms of what is feasible and what is, what might be, not really technically feasible. And I think you have to look at in the space, for example, I had this table that I showed at OIF where, for example, let's say hypothetically you could support 22 dB with a linear link. That is going to be a very small percentage of the links overall, assuming that you can even support it. So there are lots of challenges, and then there's also, of course, the 200 gig. One of the things that has happened, relatively speaking, the connector has not improved, and the PCB technology really hasn't improved in terms of the via structures, other things, very small improvements. So at 200 gig, the channels are a lot more reflective, and I give you a good example. The chip to module at the 100 gig, we use a 4-tab equalizer. 4-tab equalizer was sufficient to equalize the chip to module. And if you look at 200 gig, we did not go, blindly, to a 50 in an equalizer that has a 50 tab or a span of 50 UI. So we have gone to much more powerful equalizer to equalize the channel at 200 gig. And the reason for that is because the channel have become a lot more reflective. And in terms of, for example, the crosstalk, we have a bigger integrated crosstalk that we have to integrate. So it's a lot harder link to work with. And then when you look at the difference between a chip to module equalizer versus a KR equalizer, it's not that different. It's, if you compare those at 100 gig versus 200 gig, the KR equalizer was much more powerful.
Yeah.
So, I mean, I understand, there's all, there might be wishes and desires, but we have to also make sure that, what's being promised, it's something implementable and it could be deployed at scale,
Ali, that's an important factor. I guess you start to see more drive to linear optics. In turn, you're going to drive to bring optics on board and closer to ASIC, etc. All those problems are sort of looped together, right?
That's right. Yeah, those are all looped together. And then also time to market, development time. If I have to, if let's say you have to spend 2 additional years, you potentially may end up missing that opportunity. And I think also, as in the context here, I would say, like for example, this table, I think you definitely want to include, the RTLR or LRO in this table, because potentially, RTLR might be something that might be, more feasible, and can cover more channels at 200 gig. I do agree that, if you have a very constrained application, you could probably make the linear work, but I think those constrained applications would probably be more like a NIC cards and so on.
I was just, reflecting on this discussion a little bit, and I think that a really distinguishing characteristic of this memory coherent portion of the market is very high reliability, a very low bit error rate, and good diagnostics, which is different than what people would do for Ethernet. At least that's how I, from the conversations with the hyperscalers, that's what I pick up. I wonder if that's something we should also look at. I know these other issues are interesting to look at, but I don't think the market for this stuff will take off in memory coherent interfaces unless that's well addressed.
Yeah, no, I think it's definitely true. When you burn so much money on the ASIC itself, they don't want anything connect to it to go wrong, right?
Well, the problem is the real issue with memory coherency is if one thing has a problem, then everything that's in that coherent domain has a problem.
Yeah.
Right. So it's very expensive when there's a failure, even if it's just higher bit error rate than normal, it's just very expensive. So they need lots of margin. They need to make sure that these things don't fail. They're easy to diagnose when there's a failure. And that goes to, I think part of Ollie's comment is that, you can do this with all linear, but if you really want margin to make this more practical, something like RTLR might be a really good choice.
Yeah.
Yeah, no, I agree. I think RTLR should be part of the mix.
Mm-hmm.
I think also, if we are talking about something that runs, let's say, at 200 gig, I think at least what I've seen in terms of some of the analysis that's been done by, Mike Lees and others, they're assuming, like, for example, 75 gigahertz, like a modulators, where that type of modulator also is going to come at the premium cost. Where I think in the case of, for example, 100 gig, typically a transmitter, a modulator, or a laser of like 28 gigahertz was sufficient, and people were able to get like 40 gigahertz, modulators and EML, which were available at the time, because the 100 gig market had started 2 years earlier, and we may get there, eventually. So I think there's also that aspect where getting the sort of like getting this excess bandwidth at 200 gig, it may not come for free.
Yes, I think, Ali, what you're saying is really great. And would you mind, if possible, that can you share with some of your research about these at least on the PHY side design, the trade-off. For example, you mentioned it, the how many tabs, the reflection on the vias that could that could causing the design difficulty. And I think we should all put that into the white paper as a trade-off selection, because what you're just saying is, should we go to single lane 400 even in the future, right? Or should we just stay at 100 and then try to do like many lanes breakout to and possibly keep it on the LPO to make it overall low power and low cost, more economy, feasibility.
Right. So I think that's a very important thing to, in terms of what is speed and, should you be running this? I think the need to go to the higher speed is typically driven by the fact that there is always going to be a central processing or a central switch that needs to be 50T, and next generation need to be 100T, 200T, or 400T. And that's what drives the need to go to the higher speed, because you have this switching element in the middle. And because, like typically you're maxed out at 512 lanes, so you need to double the number of, maybe doubling the number of I/O is not practical anymore. You have to double the speed. So if you have the same type of constraint, you basically, unfortunately, have to go up this, hockey stick of, going to a higher bit rate, which is becoming more and more, difficult. But
So
if you don't
Lee, that's another good point here is the SerDes choice, right? I think
Yes.
traditionally switch tend to be limited on the perimeters of their real estate. But what I heard is if you go to like UCIe type of interface, in theory, you could actually increase let's just call it bandwidth per millimeter. Then in theory, you could use chiplets outside of your main die to increase that number of lanes. Is that a reasonable option?
I mean, you could play that game, and you could have a chiplet. Basically, what a chiplet does is, like, for example, at some point, you get a bump limited on your main die if you want to have a single radical. And if you look at, for example, like a SerDes core per lane, you probably have to have about, depending on your design, maybe around 20 bumps or so for it. And those are like typically today's at 125 micron, pitch. So that pretty much determines that, when you do a 512 lane SerDes, about 40%, give or take, of your die would end up to be the SerDes, and you're going to, you just can't put any more. And you can play the chiplet, and because the chiplet is basically what you're doing, you're expanding, right? And you could have on each side, east, west, north, south, you could put like 4 chiplets, Yeah, those things can be done, and it comes at a cost, and, reliability, also yield issue. And typically, now you would have to use something like a technology like a CoWoS or something, because you need maybe something that's a 20 micron or 25, interconnecting those two die, But yeah, that could be one thing to increase the number of SerDes. But then you still have the issue of, so now you solve the, putting more SerDes on the chiplet. Now you have to still be able to get, let's say I put down 2,000, plus SerDes. Now I still have to somehow connect that through the package and route it. So now you're running into that issue, because the package is becoming an issue as well.
Right. Again, this is an overall system constraint, but
Yeah.
I think in this scale up domain, certainly we're talking about expanding number of GPU can be interconnected. And here you're going to need a lot more channels. to interconnect together with minimum number layer of switching. So I think
Right.
there is already a bottleneck. Like how many lanes can you do in one layer of switching, right?
Right. So my understanding was that if this is some kind of memory, typically the memory gets connected to the GPUs. So it's a more of a point-to-point connection, and the issue I thought was more about ability to connect more GPU, or not GPU, but more memory to GPU. But you get basically right now you could put, like, for example, like a 3 HBM on each side. So I thought that was more the limitation, or are we trying to do something different?
Just use your example. Basically, you have a limit per, we call it memory coherency earlier, Jeff said.
Mm-hmm.
Per GPU, basically, you have fixed amount of memory. Now, if you need a certain size of memory at a certain point, you basically want, I mean, using UA link example, you want 1,000 GPU in one single layer switching, right? That's basically the proposal there.
Okay. Okay. So
Right. So you're
we're
gonna
not
need that
talking
many
about the
ports to
HBM.
interconnect
Yeah. So we are
GPUs.
not talking about the HBM attached to a GPU, but we are trying to basically build in a scale-up network.
No,
Right.
GPUs still attach at HBM, but you need a total aggregate amount of memory to.
Yeah, I think he's just saying that we're interconnecting accelerators with these links. That's what we're doing in this project.
Yes.
Right?
Okay. Okay. Not the actual HBM.
Mm-hmm.
Right.
Because the HBM will get connected directly to each GPUs. Yeah.
But Ali, I think you can use the experience you have with connecting HBMs to a GPU die.
Right.
As you know, a lot of the interfaces are normally parallel. They're not
Yes.
SerDes. Lots
That's
of wires come to an HBM.
Right.
Now, consider instead of HBM, you have a different chiplet that does the E2O engine.
Mm-hmm.
So a lot of parallel wires come in with the same pitch that you mentioned, the same bump pitch and all those issues that you said.
Right.
But when it exits the package, it exits using light or photonics.
Right. Right.
So that the same problem now translates into, okay, now how many of these chiplets I can have and how many fiber links I can egress out of.
Yeah. My recollection was, at least in the case of like NVIDIA, I thought there was almost maybe around 5-10x more bandwidth in the HBM than they use for their NVLink, and then there's another 5x. So this would be something like an equivalent, trying to build an optical fabric equivalent to like an NVLink does today with copper, I guess. Is that the application?
No, Ali, that discussion is the escape connectivity there, not necessarily had to be all serial up to the very high speed. That's the discussion, right? If you actually go down in speed, you actually end up more bandwidth density. You basically have more millimeter per or gigabit per millimeter or terabit per millimeter using lower speed. But that also saw a problem for ASIC, but also saw a problem with switch if you are willing to go that path.
You mean to go to the lower speed?
Yeah, go lower speed, escape out of the die. But then, if you want to go serial, you use a chiplet to do the SerDes going out.
So you're using like an optical chiplet, right?
Well, yeah,
Yeah,
I think he's saying it's a slow white interface off of the main die, and then a chiplet that then has the SerDes and optical conversion in it. So it's slow
exactly.
white.
And then you can
slow white to
decide
the
what is
optical
local,
engine.
what is go off. That way you sort of break this limit, forcing, I guess, SerDes keep doubling every 2 years. I think that's already started to become very, very challenging.
There's another key benefit, Ryan, and that is that part of being able to use a linear optics is a good electrical signal coming in, and at these higher speeds, and we talked about going to RTLR. I think in the end, if you look at it and you want lots of margin for these interfaces, if you do what you said with a slow white interface to an optical chiplet, then you get a really good clean signal at the optical transmitter. So you end up with probably an overall more robust and lower power solution.
Right. No, those are all good. I would call it not available today, but what is feasible in the future kind of discussions.
Yes. Yeah, so today we have many great discussions, and I hope we can continue that next week. We are overtime a lot, like 26 minutes, but it's great. I hope for people who cannot attend earlier, or have to drop early, you can watch the recording. We'll continue to discuss next week, and I'll reach out individually to discuss if you are able to contribute a little bit more into the white paper, or share the knowledge in here.
Well, before we close, I think we just talked about leaving the die and then leaving the package. At some point, all these fiber links need to leave the chassis as well. So is there some consideration on how many of these plug-in modules we can have on the edge of for example, a standard PCIe I/O plate? How dense can we be there?
Yes. I think that's a good part, because I think this is part of the Karen's discussion in here. For example, how many pins that they can break out in here. I'll find out if there has been some research in the OIF that maybe people would be able to share somewhere here, and then we can talk, deep dive a little bit further in the future. Great. Thank you, everyone, and we'll see you next week.
Thank you, Bobby.
Bye.